Everybody. So just now we talk about the dual nature of radiations, right? Dual nature of light. That means light has wave nature, light has particle natures. All right. So talking about the wave nature, just to give you a summary, light has the phenomenon such as interference, diffraction and polarization tells that light has wave natures, right? And then the phenomena such as just now we discussed, photoelectric effect, quantum effect tells that light has a particle nature. So that means the light has now two natures, all right? So depending on experiments, depending on the particular the situations, light behave. If a light is allowed to pass through a slit, light behave like a wave. If a light is meant to interact with the matter, light behave like a particle. So this is what we have. So in a way, now light has particle nature as well as wave natures. Now next, now the point is, in a nature, entire nature is made up of two entities. All right, one is energy and another one is matter. Matter and energies. Energy in a sense that a light is form of energy we talk about, and the matters. If light, which is energy forms, has dual natures, now the question is, what about matter? All right, what about matter? All right, so this kind of observation was first, this kind of question was first asked by a Department, right? So we say that, normally we say that the universe is very symmetry, right? So if it is symmetry, if matter behave like wave as well as particles, all right, matter, if I say if light behave like a wave as well as particles, I ask is why not matter? All right, so we know that entire universe is made up of two entities, energy and matters. All right, so this was asked by him, and he says that yes, matter act like wave also. All right, matter may behave like a waves. No doubt that matter has a particle natures. Right? Matter has a definite energy. If I allow a matter to fall, move with some velocity, it has a definite energy and it has definite momentum, no doubt. Now, what about particle wave natures? So he has given a hypothesis called a de Broglie hypothesis. He said that every moving matters are associated with de Broglie wavelengths. Every moving matters, all right, are associated with some wavelength. And the question is, why don't we see, right, the moving moving ball, right? Why don't we see the wave natures, right? Yes, it is very, very small wavelength. Wavelength is beyond our observations. So now where this phenomenon, where this concept is applicable, a significance, then the answer is yes, it is very much significant in a very subatomic particles. Let's say electron, let's say protons. Electron has, when I allow electron to move with some velocities, electron will have some definite, measurable, finite wavelength. And if I allow proton to move with some velocity, the proton will have some definite, finite momentum or finite wavelength. And then he proposed an hypothesis saying that the wavelength associated with particle is given by this. So this is it. He says that the particle. He says that I have a particle of mass m. Let's say the elementary particle, a very small particle of mass m, and moving with the velocity v, and it has a momentum. And he says that this particular particle has a wavelength that is given by h by p, or this is equal to h by mv. So this is what we so a wavelength So wavelength is given by this. This is a wavelength, and this was first proposed by de Broglie. This was simply a hypothesis. This was simply a hypothesis, and then he says that now look at here. When we use this hypothesis and apply it to a light, and we'll be able to see that we will be able to reproduce some formulas, right? So this is the momentum of light. This is the momentum of light. So when I use these equations, h divided by momentum, that is h mu divided by c, cancel out, and c goes up, c by mu. And what is c by mu? C by mu is lambda. Why? Because we know that relations, right? Mu by lambda is equal to c, that is the speed of light. From we can get this from Maxwell equations. We can get this relation from Maxwell equations. So we say that for the de Broglie hypothesis, the de Broglie equation could able to tell that the light particle has wave natures. A light particle has a wavelength which is exactly same as the Maxwell equation. So this is what we talk about. All right. So this is very much consistent with photons. All right. So this is equation, right? So we say that, and these kind of observations are very true, very measurable only with elementary particle or only with subatomic particle. So this is what we call as a de Broglie hypothesis. This is what we call as de Broglie hypothesis. Photons, and this is the wavelength. Right? So therefore we say that every moving particles has some wavelength, and the wavelength is determined by. So this equation also tells us that. Look at here. This is Planck constant, which is very small, of order of 10 raised to the power minus 34. All right. Therefore, if a finite mass, let's say I have 50 grams, right? I have 50 grams is moving with 20 meter per second. Then this is equal to 1000, right? That means 1000 kg, right? So therefore, the wavelength is going to be 10 raised to the power minus 34 meter, and this is extremely very small wavelength. See, if I say 50 gram of an object is moving with 20 meter per second, so wavelength we get is 10 raised to the power minus 34, which cannot be measured by any device. So therefore, we won't be able to see it. But what about in case of electron? That you can do this in a room, right? So electron has a wavelength that is of order of 10 raised to the power minus 10 meter, right? All right. So therefore, it has a finite wavelength. Now, how to measure, right? How to measure wavelength of electron? We can't see electron and we cannot measure the velocity. How to measure? So that this is again a little simple. Let's say I have electrons. This is an electron. I isolate electron with potential. Let's say this is the potential, and we will be having a potential. Let's say this is the potential V. If electron is accelerated with a potential V, and then amount of energy electron has is this much energy. This is energy, and this energy is in form of kinetic energies. This energy is in form of kinetic energy, and which can be written as, all right, where m is the mass of electrons and v is the velocity of electrons. All right, so therefore this is what we talk about. This is what we talk about. I say this is what we talk about, and I just divide and multiply by m. Okay, and we get momentum, right? What is that? P square is a momentum, right? We got P square. So now we got momentum. How much is momentum? Momentum is EV divided by 2m square. This is the momentum. This is the momentum. V is the moment. V is the potential. Let's say V is the potential, not a velocity. V is the potentials. V is the potentials. All right. So now, if this V is the potential, right? If V is the potential, now let me do this, right? Kinetic energy is momentum is this much. Now I would like to figure out that what is EV? EV is a kinetic energy, right? EV is a kinetic energy, right? And now what I'm going to do, this is the kinetic energy and is equal to EV, right? So now when I use this and then I use the de Broglie wave equation. De Broglie wave equation is given by h divided by p. I substitute the value of h, p. When I substitute the value of p, what I'm going to get is h divided by root of EV divided by 2m. All right. Finally, what we are going to get is, I put all the value, and finally what we are going to get is h. I'll say this is h root of 2m divided by EV root whatever, right? So if h is a Planck constant, fixed value, m is a mass of electron, fixed value, E is a charge of electron, fixed value. If I put all the value, finally what I got is this is 1.227 divided by root of V and nanometer. So this is the wavelength. So this equation tells that if potential is higher, then wavelength is going to become smaller. Why? Because momentum increase. If a potential increases, the velocity is going to be greater and the momentum is going to increase, and then the wavelength is going to decrease. Alright. So now if I give you an example, for potential of, let's say if V is equal to, let's say if V is 120 volt, then the wavelength is in order of 0.112 nanometers. So this is the wavelength. So this is the wavelength of electrons. This is the wavelength of electron when electron is kept under a potential of 120 volt. 120 volts. So this is one very, very important. Alright. So this is how we could able to measure. So therefore, how to measure momentum? Now, how to measure the wavelength of electrons is very simple. This is 1.227 divided by root V nanometer, where V is a potential. Where V is a potential. And then the wave nature of electron was found by the two scientists, that is Davison and Germer experiments. And Davison and Germer, they collectively found that the electron has wave natures using X-ray crystals experiments, what we call as crystal diffraction methods. And then de Broglie was awarded Nobel Prize in year 1927, right? This is what we talk about. So this is what we talk about, the wave nature of particle. Now next what we would like to do is another, a very important characteristic or property of what we call as subatomic particles. All right. If you go down to a subatomic particles, you see a different nature, right? All right. The object or the nature doesn't see the nature that we see around. The nature is completely different when you go down to a subatomic particles. That is what we call as a Heisenberg uncertainty principles. So maybe you have learned this in the chemistry, right? So we say that whenever we talk about particles, we talk about two important things: positions and momentums. We talk about two positions, two concept or two entity. That is what we call as a position and a momentum. So that the uncertainty principle says that it is not at all possible. In nature, it is not at all possible to measure, all right, exact momentum and exact position at the same time. All right. In a nature, it says that it is not at all possible to measure exact momentum and exact positions of a particle at the same time. It is not due to the limitation of an optical particular instrument. It is all because of nature, right? All because of nature. Nature doesn't allow us to know, to measure the momentum and the electron exactly at the same time. And he says that delta x is what we call as uncertainty in a positions. Uncertainty in positions. This is what we call as uncertainty in a positions. And delta p is uncertainty in a momentums. So he says that this uncertainty, these two uncertainty is an order of h by 2 pi. Again, this is whenever we deal with the subatomic particle, we frequently come across Planck constant. So Planck constant is a constant that defines subatomic particles. So this is the equation. This is the uncertainty equations. So the product of the uncertainty in the positions and uncertainty in the momentums is always order of h by 2 pi. H by 2 pi. Sometimes we write this as h bar. This is again h by 2 pi. So this is one very important, right? So now look at here, right? Now we would like to combine Heisenberg uncertainty and de Broglie wave equations. Let's say that if I say that this is definite, that is uncertainty in a momentum is 0. That is momentum is definite. That is momentum is definite, right? The momentum is definite, right? Momentum is definite. Momentum is definite, and there is no uncertainty in a momentum. So this implies that delta x is infinity. Delta x is infinities. Delta x is infinities. That means you cannot localize. You cannot say that electron is at the x is a position. Delta x is the uncertainty in a position. If delta x is infinity, the possibility, right? The probability of finding electron is everywhere, right? Everywhere in the universe. Everywhere in the universe. That's what we talk about. And now if I say if delta x is 0, right? If a position is finite, if a position is definite, which implies that delta p is infinities. Alright? So delta p could have the electron could have any value of velocities. Electron could move with any particular velocity. So that's what we talk about. Now what we are going to do is we are trying to figure out this in a de Broglie wave equations, right? Let's say now I shall take these equations. I shall take this, right? Now let's say that momentum is definite, and then position, the uncertainty in a position is infinite. If a momentum is definite, then de Broglie wave equations, alright? That means if each particle has a definite or a single wavelength. single wavelength. Alright, this is a single wavelength. And it also tells that this single wavelength is the probability of finding that particle is everywhere, right? So that means it is delocalized, right? So we say that, so this is, alright, and since I write this, since this is tends to infinities, alright, you say that electron is found everywhere, right? Electron is found everywhere, right? Because it is, electron is found everywhere. Electron is found everywhere, right? So this is what we talk about. So you will have a single wavelength. If I figure out in terms of a wave, you find that particular particle can be visualized like a wave, single wavelength, extended everywhere, right? Or I say this single wavelength, all right, extended everywhere, right? Everywhere, right? So this is what we talk about. This is what we talk about, right? So this was explained by another, another concept. This is what we call as a Born probability interpretations. Born probability interpretations. So Born probability interpretation says that if delta x tends to infinity, if delta x tends to infinities, all right, then electrons, all right, electron is found everywhere. That is electron is not localized, right? Position of electron is not localized. Position is not localized. Extended all over space. Or I say that position of electron is extended all over space. Extended all over space. Which is not true. Right? So if it is so, then Born probability interpretation says that yes, this is electron is found everywhere, that is position is not localized, and then extended, and the electron is extended all over space, which is not true. All right. Then how to explain? Right? Then explanation is that delta t cannot be 0, delta x cannot be 0. All right. So therefore we say that the matter, right? The matter wave associated with electron is not extended everywhere. It is localized at particular finite space. It is localized in a particular finite space. And we could able to explain this in terms of what we call the wave package. So this is what we talk about. Now this particular matter wave is extended over certain region, right? And that is how it is that, right? So the matter wave associated with electron is not extended all over space. And now we say that if a momentum is not definite, it has some different momentums. So therefore wavelength could be of different, right? If it is so, you get a different wavelength. There's no single wavelength, all right? And if it is not equal to 0, and if it is not tend to infinity, I say if delta is not tend to infinity, then it is extended to a certain region, right? So this is what we call as a wave package. So the Born interpretation says that it is not at all possible to say that momentum, the uncertainty in momentum cannot be 0, uncertainty in a position cannot be 0, uncertainty in a momentum cannot be 0, uncertainty in case of position cannot be 0, should be some finite value. If it is so, then the positions, right? of electron is confined or localized in a certain region, right? In a certain finite regions with a different waves, with a different wavelength. All right. So this wavelength, this pattern is what we define as a wave package. All right. So it is a wave package extending over some finite region. So that means that now electrons are. We cannot say that electron could be at that particular position. So we say the electrons are found within these regions. The probability of finding electron is in these regions. Alright. So probability of finding electron in these regions. Alright. Probability of finding electron in these. So you cannot say that electron is at that particular point. We say the electron is found within these regions, right? So if amplitude is greater, the probability of finding electron is more. So this is what we call as a wave package. All right, this is what we call as a wave package. So in a way, so this is what what I talk about. This is a single wavelength extended everywhere in the universe, everywhere all over the space, which is not true. It is the wave packet, all right, extended only in a certain regions, only in a finite regions. Now this is the point, right? So now what I would like to do now here is the uncertainty principle. Heisenberg uncertainty principle is outcome of de Broglie and Born interpretations and wave packets. So we say that the Born relation says that the de Broglie says that electron has momentum, right? Electron has momentums. Electron also has a spread out momentums. Electron has a momentum, and we say the electron cannot have a definite momentum. The electron has some spread momentum. That means you cannot. There is the uncertainty in a momentum value, right? And that's what we talk about. Why these equations? H by P, right? So this is not going to be a P. Will have some delta P. Delta P is what we call as uncertainty. And the Born interpretation says that this P cannot be zero. Cannot be zero. P cannot be zero, right? All right. P cannot be zero. If a P cannot be zero, then I say that electron must found within certain finite regions, right? That is in the form of wave package. So therefore we say that the Born the de Broglie relations and the wave package descriptions together with the Born interpretations, Born probability interpretations predict what we call as a Heisenberg uncertainty principle. That's this. All right. So this is what we talk about. So now what I would like to conclude here is, yes, electron has a wave nature, electron has a particle nature, all right, and this is the foundation of what we call as a quantum mechanics. So electron has a wave nature, electron has a particle natures, and light has a wave nature, light has a particle nature. All right. So maybe it is little tough to understand, but you go through our text. And then one more I would like to ask is, we have so many examples in this particular book. Try to do all the example as a home assignment. Thank you.